Hello, welcome back to the second course in physics. And now we will be in this lecture talking about the electric circuits. In the previous lecture, we have defined the electric current and the resistances and all the elements and ingredients required for circuit analysis and for the circuits. And now we will continue doing this, and we will touch on some of the principles that are related to the electric circuits and relevant to the analysis of the electric circuits. The contents of this lecture will include some historical introduction, and then the definition of the electromotive force, and then the derivation of the loop current, and then we will discuss the Wheatstone bridge as a tool for measuring the an unknown resistance by the null method, and then we will state Kirchhoff's laws. The first law, which is a consequence of the charge conservation, and the second law, which is a consequence of the energy conservation, and then we will consider some applications of these laws for circuit analysis, for a simple case of circuit analysis, and we'll leave the more general and more complicated discussion to another lecture. In the beginning, we should mention that the scientist Gustav Robert Kirchhoff has set up and derived two fundamental laws in 1947 and in 1948. And those two laws, the so-called Kirchhoff's laws, form the basis for the circuit analysis in the steady state, in the direct current circuits. These two laws are so fundamental and important that we will see in the next lecture or so, and they are truly the pillars of the circuit analysis. One law, as I mentioned just a little while ago, one law of these is based on the principle of charge conservation. Charge cannot be created or annihilated. And the second law is based on the principle of energy conservation. Energy pumped into the system appears somewhere else. And now, at the beginning of this circuit analysis, we have to touch on a very important concept, which is the electromotive force. This is so important in circuits that deserves to discuss in a little details. In the steady state, where current is constant in a circuit, a fixed potential difference across a resistor, if we can maintain across a resistor a fixed potential difference, this fixed potential difference across the resistor will introduce or will result in the flow of a steady constant current across the resistor. But in order to maintain the potential difference across the resistor, we need some sort of a charge pump that keeps pumping the charges, because the charges, once the charge reaches one end of the resistor, it just goes down the resistor, and you need to pump it again. So this pump, this charge pump, this device, is called an electromotive force device. It works like a pump for the charges. It's similar to pumping water to a higher place, where the water then goes down and does work across, and then you have to pump it again. So the electromotive force as a device could be viewed as a charge pump. What is the principle of the operation of the electromotive force? In most common devices, the source of the electromotive force is one type or the other. And let's look into these. For example, the battery. What is the source of the electromotive force? The source of the electromotive force is chemical. There's a chemical reaction there that maintains a fixed potential difference between the two ends of the battery. So the source is chemical in the battery. In the electric generator, the source is mechanical, where we have some sort of mechanical motion that introduces some potential difference. And in the case of the solar cells, the source of the electromotive force is solar energy, which is converted into potential difference. And in fuel cells, again, the source of the electromotive force is chemical. That is the source of the work done, or the pump, the work done to pump the charge. And in the thermopiles, a temperature difference is the source for maintaining the potential difference or the electromotive force across the device. Now, an electromotive force does work actually in pumping the charges. It does work to drive or to move the positive charges from the lower potential to the higher potential inside the electromotive force device. And that's why we call it like a pump, because it moves the charges in an opposite direction to the natural way. Naturally, the positive charges like to drop from a point of higher potential to a point of lower potential. However, across the device or inside the device, the charges move from the positive charges move from the lower potential to the higher potential. It's like pumping them up. And thus, the device should do work in order to pump the charges up. It introduces work into the system. So this is a figure that shows the loop, and this shows a resistor that is connected across a seat of electromotive force or an electromotive force device. Epsilon here is the electromotive force of the device, and as we connect the resistance R across the two ends, between the two ends of this device, the charges, positive charges flow, making up the current, resulting in the current across or through the resistance R. And as the current or the positive charges reach the negative terminal of the device, the electromotive force does work to pump the charges up from the negative terminal to the positive terminal. And then the charges go naturally through the resistance, because the this point in the resistance is at higher potential than this point, and thus the charges just drop naturally across the resistance. And the work done inside the seat of the electromotive force or the electromotive force device, the work done per unit charge is the definition of the voltage of the electromotive force. It is a voltage, of course, it's a unit of voltage, but it's the electromotive force. So it's defined as the work done to move a unit charge. It's the rate of work done per unit charge to pump the charges from the negative terminal to the positive terminal of the electromotive force device. In an ideal device, we speak of a device, an electromotive force device, where it doesn't have an internal resistance. In this case, the potential difference between the terminals of the device, the potential difference is equal to the electromotive force, because all of the work done to pump the charges from the lower potential to the higher potential end of the device is all consumed in moving across the electromotive force epsilon with no work done, with no work being lost or dropped across an internal resistance if the internal resistance does not exist. So in that case, the potential difference between the two terminals of the electromotive force device is equal to the electromotive force epsilon. And that way we see that epsilon has units of voltage. It's like a voltage difference. In the case of a real electromotive force, however, real devices do have internal resistance. No real device has zero resistance. So since it has an internal resistance, then some of the work done in pumping the charges will be a drop or dissipated across the resistor, the internal resistance of the device. And thus, the potential difference that appears between the ends of the battery or the electromotive force device is lower than the electromotive force, because the electromotive force is divided, actually, in this sense, is divided into a potential difference between the two terminals and as a potential drop across the internal resistance of the device. And now let's use these concepts and definitions to evaluate a loop current if we have an electromotive force device that is connected to some resistors in a loop in a circuit. Let's calculate the loop current. If we have, for simplicity, a single loop which contains an ideal electromotive force device, as a simple first example, in this case is depicted by this figure, where we have a seat of electromotive force or an electromotive force device connected by wires to a resistor with resistance R, and there is accordingly a current flows because of the charge pump through the circuit by the electromotive force. Charge is going through the circuit, and it forms a current that is equal to I, the current I. Now, if we follow the potential from point A and going back to point A, what do we have? We have the potential at point A, V sub A, and as we move from A to point B, we encounter the electromotive force. And the electromotive force is positive in this direction because we go from the lower potential to the upper potential. So we increase, we go up in potential. So VA plus epsilon, we gain potential, we go up, plus epsilon. And then here there is no potential drop until we reach point C. And point C is at a higher potential than point D, and that's why current goes down the resistance. So we have minus, we go down in potential, minus the voltage across the resistor, which is IR. So we have minus IR, and by that point we reach D, and D is at the same potential as A because there is nothing in between. The VD and VA are the same. So this should equal to VA. So we start with, again, start with A, VA plus epsilon minus IR, that is equal to this potential, V sub A. V sub A exists in both sides, and this gives us the facility to calculate the loop current accordingly. I times R is equal to epsilon, which gives the loop current I is equal to the electromotive force epsilon divided by the resistance. This is a simple example of calculating the loop current using an ideal resistor, an ideal electromotive force device with a single resistance in the loop. And now if we have a real electromotive force device, in this case the device itself has an internal resistance, small r we call it, in order to distinguish it from the load resistance, capital R, that is connected with the device. And again, the current is flowing in the circuit, and we can calculate the loop current, and also we can calculate the potential difference between the two terminals of the electromotive force device. The electromotive force device contains both the electromotive force epsilon plus the internal resistance R. It is inside, within, and this is depicted by this square here. And the potential difference between the terminals, we can calculate the potential difference. We start from the negative point at V negative, and then we go up as we go from the negative terminal of the electromotive force to the positive terminal. We go up in potential, so we gain potential. So we have plus epsilon, and as the current goes across through the internal resistance R, it goes down from a higher potential to a lower potential end of the resistor. It's in a natural way, so we lose, as the current goes through a resistor, we lose this kind or this amount of voltage or potential, so minus IR, and by that time we reach the positive point. So this should equal the voltage V sub A. The summation of all the voltage starting from V minus, the summation of all the voltage until we reach this point will equal to the voltage of this point. So that means the voltage difference between the positive terminal and the negative terminal of the whole seat of the device is equal to V plus minus V minus. By definition, this is equal to V, the potential difference between the two terminals, and that is equal to the electromotive force epsilon minus the current times the internal resistance. So as we notice from here that it looks like the electromotive force epsilon is divided into two components. One component is the potential drop IR across the internal resistance, and the remaining appears as a voltage difference between the two terminals or the two sides of the electromotive force device. So that's how we lose some of the potential arising from the electromotive force because it goes as a potential drop across the internal resistance. Further, now in order to evaluate the loop current, we start from one end of the device with a negative with V minus, and we go across the circuit V minus plus epsilon as we go from the lower end, the lower potential of the electromotive force to the upper potential, plus epsilon minus IR as we drop, as we go through the internal resistance. Again, minus I capital R as we go across the load resistance. And by that time, after we cross the load resistance, we reach V minus, which is the same point that we started from. And those points, V minus and V minus, they can be cancelled out. And thus, the loop current, I, can be determined from epsilon minus IR minus I capital R is equal to 0. And the result is the loop current in this case is equal to epsilon divided by the load resistance R plus the internal resistance small r. And we notice here that the current in the loop is reduced due to the internal resistance in the device itself. It's less than the current if the device were an ideal device without an internal resistance. And now we will take as a simple example on these concepts the Wheatstone bridge, a certain arrangement of a set of resistors. And this arrangement, the Wheatstone bridge, can be used in various applications. And one of the most important applications for the present discussion is the determination of an unknown resistance if we know the remaining resistance in the bridge, resistances in the bridge. So if we have an unknown resistance, we put in the bridge known resistors, and from those known resistors, we use the so-called null method in order to evaluate the unknown resistor. And this method provides an accurate method. We can determine the unknown resistance to up to the accuracy that we desire by choice of the other resistors in the bridge. And this, the principles of this will be as follows. We mention here that Charles Wheatstone in 1843 was devising this work, and the bridge looks like this, where we have R1 and R2 in one branch are connected together. R3 and R4 are connected in the second branch. And from the point between R1 and R2 and the point between R3 and R4, there is another resistor or load between points C and D. And the whole bridge is connected across an electromotive force between points A and B. This is Wheatstone bridge, and we use the null method measurement for measuring an unknown resistance. And this null method is that we suppose, for example, that R1 is the unknown resistance. We change R2, R3, and R4 We keep changing them until the current across RD is equal to 0. That is the null method. We zero the current across RD. That means there is no current flowing between points C and D. And that is the so-called null method. At this point, from this point, we can evaluate the unknown resistance, whether it is R1 or R2 or R3 or R4. But we have to have one unknown resistance, and the rest of the resistors should be known, and then we can evaluate this resistance. And by the choice of the magnitudes of these resistances, R3, R4, and R2, for example, we can determine the unknown resistance R1 up to the accuracy that we desire. Thus, as we mentioned in this case, where we have the null or the zero current, I sub D is equal to 0 in the resistor RD. In this case, we say that the bridge is balanced. We have a balanced Wheatstone bridge. Balanced meaning there is no current flowing between the two branches, R1, R2, and the branch R3, R4. There is no current, and this is a balanced bridge. So in the balanced bridge, let's analyze this circuit. In this case, we have, for example, assume that current flows from the electromotive force to point A, and then at point A, it splits into two parts. It splits into a current that goes through R1 and current that goes through R3. Now, the current that goes through R1 is called I1, and since there is no current in RD, then the same current R1 keeps going because there is no other way for it to go. So the current through R2 is also, in the case of the balanced bridge, is also I1. Again, the current through R3 that flows from A to D, we call it I3. And since there is no current in RD, then I3 has no other way to go but across R4. So that means the current I4 that goes across R4 should be the same as the current I3. So I3 and I4 are the same. Also, since there is no current flowing between C and D across RD, then we conclude that the potential of the point C, V sub C, is equal to the potential of the point D, V sub D. Because if they were not at the same potential, then current will flow in R sub D. But there is no current, that means V sub C and V sub D are equal. So in this case, we look at the potential difference between A and C, and we say that this potential difference between A and C is simply I1 R1. So I1 R1 is equal to VA minus VC. But since VC and VD are equal, so that means I1 R1 is equal to VA minus VD equally. But VA minus VD is equal to I3 R3 at the same time. It's equal to I3 R3. So that concludes, we conclude that I1 R1 is equal to I3 R3. This is the first equation that we need. And similarly, we have I2 R2, the current flowing through R2, times R2, I2 R2, is equal to VC minus VB. But since point C and point D are at the same potential, so VC is the same as VD. So this I2 R2 should equal also VD minus VB. But VD minus VB is the current I4 times R4. And I4 is equal to I3, as we mentioned a little while ago, and I2 is equal to I1. With this replacement, we reach I2 R2, which is the same as I1 R2, is equal to I4 R4, which is the same as I3 R4. So this is the second equation. And now we have these two equations, I1 R1 equals I3 R3, and I1 R2 equals I3 R4. And we can divide these equations and we obtain the result for the balanced Wheatstone bridge. The ratio of R1 to R2, R1 over R2, is equal to the ratio R3 over R4. So the ratio of the first resistor on one branch to the second resistor in that branch is equal to the ratio of the first resistor on the second branch to the second resistor in that branch. R1 over R2 is equal to R3 over R4. And thus, if we have any one of these four resistors, if any one of them is an unknown resistor, we can determine this unknown resistance if we know the remaining resistances. And now we move to Kirchhoff's laws, those fundamental laws for circuit analysis. Kirchhoff has lived in the time between 1824 and 1887, has done quite a job and a very important job in developing these two fundamental laws. And the first law says or states that the sum of currents entering any junction in the circuit must equal to the sum of currents leaving that junction. So if we go at any junction and we add the currents that are entering the junction, that is equal to the sum of currents leaving the junction. So if we have a sign convention, some sort of a sign convention, like for example, the currents entering are positive and the currents leaving are negative, if we sum over all the currents at any junction, the summation should be 0, because the currents entering are equal to the currents leaving. And if we assume that one of them is positive and the other is negative, then the total current is equal to 0. So at any junction, for example, in this junction that we show in the figure, I1 plus I2 is equal to I3 plus I4. This is a manifestation of the first law of Kirchhoff. And the second law of Kirchhoff, which is based on the conservation of energy, states that the sum of the electromotive forces in a loop in the circuit equals the sum of the potential drops around that loop or around that circuit. So what we do is we start from one point in the loop, in the circuit. We start from one point and we keep going, counting the electromotive forces that are in the direction of our passage. We calculate the electromotive forces, and then the summation of that electromotive forces is equal to the voltage drop across all the resistors in that loop, on that loop. So this illustrates the loop, how we go. We start from one point and we go back to the same point in the loop, a closed loop. And in a mathematical form, the summation as we go around the loop, the summation of epsilon, and we have to take the sign into consideration. So if our direction in going around the loop is in the direction of epsilon, we consider it positive. If it's in the opposite direction of epsilon, we consider it negative. And this summation of epsilon is equal to IK/RK, where IK is the current passing through a resistance RK, and RK is that resistance. So this is a statement, a mathematical statement of Kirchhoff's second law. And as we mentioned, this is a consequence of the energy conservation. That means the work done in pumping the charge appears as energy in the resistors. And for a network, let's assume that we have a circuit with a network, a number of branches and nodes that are connected in a desirable manner. In this network, if we consider that we have n nodes, capital N nodes, and if we consider that we have b branches, that means if we have b branches, that means we have b independent currents flowing in the b branches. So our circuit analysis will be to find these b currents, those currents flowing in the branches, in all the branches. And thus, we must have a number of independent equations that is equal to b, to the number of the branches. So if we have b equations, we can solve these b equations for b unknowns, which are the b currents flowing in the branches, in all the branches. So we must have b independent equations to solve the network and to find the currents in the branches. In this case, this is not a simple case like the loop, where we have one loop, one current to determine. This is, for example, in the figure that is shown here, we have 3 nodes, 1, 2, 3 nodes, and we have 5 branches. In this case, we have 5 different currents, and we must have 5 equations. So how do we get these equations? From the first law gives n minus 1 equations, because one equation comes from the first, the one equation comes from the second, where the current splits, and then the last node is usually a trivial. It's all the currents are collecting there, so it's a trivial solution. It comes from adding all the previous currents that are coming, or equations that are coming from the first law. So we always have n. If we have n nodes, we have n minus 1 equations from the first law. And from the second law, we have b minus n plus 1 equations. That is provided by the second law from the loops. Notice, like, for example, in this equation, in this shape that we have in this circuit, we have 3 nodes. That means we have 2 equations from the first law, and we have b branches, which means we have 5 branches. 5 minus n, that is 5 minus 3 is equal to 2, plus 1 is equal to 3. So we have 3 equations from the second law, 2 equations from the first law, and 3 equations from the second law. That's 5 equations. 5 equations is exactly equal to the number of branches, b. So we have, that way we have the desired number of equations to solve. And as an application, we consider identical cells connected in parallel. Across these cells, we have a load resistance R, capital R. The internal resistance of each cell is small r, and the electromotive force of each cell is epsilon. So they are identical cells. And in this case, we have 2 nodes, which are A and B. These are the only 2 nodes that we have, A and B. and we have n plus 1 branches, because we are assuming that we have n identical cells, small n identical cells. So these are providing n branches, small n branches, and we have another branch which is the load resistance R as a branch, so n plus 1 branches in total. And thus, from Kirchhoff's first law, since we have two nodes, we will have one equation, and that equation states that the total current I is equal to I1 plus I2 plus I3 plus I4. It's equal to the sum of the currents going through all the branches. That one equation comes from the first law. And now, from the second law, from the Kirchhoff's second law, we have small n equations, because we have n plus 1 minus 1. That means we have n equations. N minus 1 equations are coming from these loops, which are formed by two consecutive cells. So, for example, between the first cell and the second cell, this loop gives us the first equation and gives us I1 equals I2. And the second loop gives us I2 equals I3. So, essentially, we have n minus 1 such equations, which gives you I1 equals I2 equals I3 until equals In. And that gives us the result I sub k, I in any branch, is equal, which we call I prime. So the total I from the first equation, from the total I is equal to the number of branches, which is small n, times I prime, the current in each branch. And also, we have one equation which can be obtained by taking a loop through the load resistance and any one of the cells, any one of the branches of the cells. So let's assume that we are taking the branch of the cell number 1. So epsilon is equal to R I1 plus R, capital R, the load resistance, times I that's going through it. And that is equal to R times the total current I over N, because here we have replaced I1 by I over N, which is plus the load resistance times I, and then the current through R is determined as I is equal to epsilon over R plus R over N. And here it is worth mentioning that the n cells are in parallel. That means their equivalent resistance is 1 over R naught is equal to the summation of 1 over Rk, which is simply equal to n times 1 over R, the resistance of each one of them. And that means R naught is equal to R over N. And the equivalent electromotive force, epsilon naught, we call it, is equal to R naught plus capital R, the load resistance, times R, times I, which is R over N plus capital R times I, which is equal to epsilon, which means that we have the electromotive force of the parallel set of seats is equal to the electromotive force of an individual one, but the current through the load resistance driven from the parallel set increases. It is larger than the current that we can draw from a single cell. And by this, we finish this lecture, and thank you for your attention.